Welcome to this explainer. Today we're unpacking lecture 5, and honestly, we're going to have to play mathematical detectives to investigate some crazy network structures and try to solve a massive logical paradox. We're going to dig right into the hidden architecture of graphs, look at what exactly holds them together, and then tackle a proof that seemingly breaks the fundamental rules of math. Here's our roadmap for today. We're looking at the longest path trick, then bridges and cut vertices, moving on to dominating sets, and finishing up with Brouwer's paradox. Let's kick things off with section 1, the longest path trick. All right, so our very first tool is proposition 1.1.1. Informally, it's known as the longest path trick. It's basically our go-to strategy for finding closed loops inside any network. The notes give us this rock-solid guarantee. If every single point in a network has enough connections, specifically a degree of at least d, where d is greater than 1, then a closed loop or cycle of length d plus 1 absolutely has to exist. It's structural magic based entirely on how connected those individual points are.
So how do we prove this? The logic is actually beautifully simple. Imagine you just start walking along the edges of your graph, and you literally just don't stop until you hit a dead end. Boom, you've just formed the absolute longest possible path. Now, think about your starting vertex. If it had a neighbor that was sitting somewhere outside this path, well, you could just walk to it and make the path even longer. But we just said this is the longest path, right? So logically, all of its d neighbors must already be sitting somewhere on this exact path.
And that is what makes this trick so brilliant. Because all the neighbors of that starting node have to already be on the path. Eventually, one of those connections is going to link right back to an earlier point. By tying the beginning of our path back into the middle, we completely trap our cycle. It's a guaranteed loop. Moving right along to section 2, bridges and cut vertices. So now that we know how to track down these cycles, what actually happens if we start cutting connections? This gets right into the structural vulnerabilities of a network. Theorem 1.2.2 draws a very hard line between two specific types of edges. If you remove an edge that's part of a cycle, you essentially just leave a detour. The graph stays perfectly intact because, you can just take the long way around the loop. But if you remove an edge that doesn't belong to any cycle, which we call a bridge, you literally fracture the network. You increase the number of disconnected components. It's like a single internet cable connecting two islands. If that snaps, the connection is entirely gone. Take a look at what happens when you remove an edge, let's call it edge A, that happens to be part of a triangle cycle. The graph safely stays in its original 4 pieces. The points that used to be connected by A can still totally reach each other. They just have to travel through the other sides of the triangle. But watch what happens next. If we completely sever a true bridge, let's call it edge B, which has absolutely 0 alternative detours, the number of components instantly jumps from 4 to 5. The vertex sitting at the end of edge B is now totally stranded. We've physically broken the network. Now, edges aren't the only weak points here. What if we target the nodes themselves? Removing a single node, known as a cut vertex, can honestly be way more devastating than taking out a bridge. Why? Because when you delete a vertex, you instantly wipe out every single edge connected to it, the whole shebang. Think about the star graph example from the professor's notes. You've got a central vertex connected to 4 outer points. If you remove just that one single center cut vertex, it instantly shatters what was one connected network into 4 completely isolated, floating pieces. It is a totally catastrophic failure of the entire network structure. All right, section 3. Dominating sets. Let's see how this structural knowledge feeds into our next detective concept, surveillance and control, or mathematically speaking, dominating sets. The best way to think about a dominating set is like trying to place security cameras in a massive building. For a set of vertices to actually be dominating, every single node in the entire network must either have a camera placed right on it, or it has to be directly connected by just one edge to a node that does have a camera. Absolutely no vertex is allowed to hide out of reach. Now, the density of your network completely changes the game. Sure, you could just select every single node, and that works, but it's wildly inefficient. If you have a complete graph where literally everyone connects to everyone, you just need one single camera. Easy. But isolated vertices, the ones with 0 connections, those force your hand. You have to include them directly in your set because literally nobody else is watching them. Oh, and here's a neat rule. If a graph has no isolated vertices at all, you can always dominate it using at most half of the total nodes. It becomes a real puzzle of efficiency. Can you spot where the dominating sets would be? If you drop a camera on one specific vertex, you might instantly observe 2 or 3 others. Depending entirely on the network's shape, you have to be super strategic, picking nodes so that absolutely no vertex is left unmonitored. Which brings us to our final and, frankly, most mind-bending topic. Section 4, Brouwer's Paradox. This is where the source material drops a real mystery on us. We're talking about a theorem that makes an incredibly bold claim and then just seems to utterly defy logic when we try to prove it mathematically. Theorem 1.3.5, Brouwer's dominating set theorem, states that no matter what your graph looks like, the total count of valid dominating sets you can find inside it is always an odd number. Never even, always odd. Okay, so how on earth do the notes prove this? Well, they introduce this massive theoretical supergraph called H, and this is wild. In this graph, the vertices aren't even individual points anymore. They are entirely different subsets of our original graph. We only draw an edge between these subsets if they form what's called a detached pair. That basically just means there are absolutely zero connections between subset A and subset B back in the original graph. The mathematical proof maps this out so beautifully. It calculates the neighbors of these subsets and uses powers of 2 to demonstrate this flawless equivalence. It shows that a subset is a dominating set in our original graph if, and literally only if, it has an odd degree, meaning an odd number of neighbors, over in our giant supergraph H. But wait a second. Do you remember the handshake lemma from back in Lecture 2? That lemma explicitly, mathematically proves that any simple graph, and yes, that includes our giant supergraph H, absolutely must have an even number of odd degree vertices. Okay, so here is the absolute crux of the issue. Our proof just definitively concluded, relying on the handshake lemma, that there has to be an even number of dominating sets in any graph. But that is the literal exact opposite of Brouwer's theorem, which tells us it's always odd. We have just mathematically proven a complete contradiction. And the explainer notes literally just drop this on us as a cliffhanger homework assignment. The step-by-step logic we just walked through looks entirely flawless. The mapping of the dominating sets seems perfect. The handshake lemma is an undisputed, rock-solid fact of graph theory. So where exactly is the fatal flaw? I'm going to leave you with that provocative thought to chew on. Retrace our steps, look really closely at the rules of those detached pairs, and the very definition of our giant supergraph H. What hidden assumption did we make that broke the fundamental rules of math? Dive into those subsets and ask yourself, what did we miss?